Hi, today I'm going to talk about network characterization of the Western US power grid as a part of Lab 1 for ECE 519. So here I will walk through the dataset, the methodology used for analysis, the evaluated network parameters, and the key insights derived from both quantitative metrics and visualization. This dataset represents the Western power grid of the United States. In this network, each node represents a power station or a substation, and edge exists between two nodes if there is a transmission line connecting them. So this is a physical infrastructure network. It models real electrical connections, not social interactions or digital communication. The data source is the Western US Power Grid dataset, which is publicly available. The file format is GML, which stands for Graph Modeling Language. This format stores nodes and edges in a structured way that can be directly imported into network analysis tools, which is really easy because this is a real infrastructure system. We expect the structure to reflect geographic constraints and engineering design decisions. Now, I will summarize the structural characteristics of the network. This slide actually summarizes the main structural properties of the network. First, the domain is electrical power infrastructure. This means the network represents a real engineered system with physical constraints. The graph is undirected and unweighted. Undirected means the connections are modeled without direction. Unweighted means we only represent whether a connection exists, not its capacity or flow. Nodes represent power stations and substations. Edges represent transmission lines connecting those stations. The network contains 4,941 nodes and 6,594 edges. Given this size, the number of actual connections is very small compared to the number of possible connections. This suggests that the network is sparse. Finally, this dataset represents an engineered infrastructure network. We expect its structure to be shaped by geography, cost, and reliability considerations rather than random formation. Next, we will briefly talk about the tools and methodology used for the analysis. For this analysis, I used Python as the programming language. For network analysis, I used the NetworkX library. NetworkX provides built-in functions to compute structural metrics such as degree, clustering, diameter, and all. For numerical computation such as averaging, centrality values, and handling arrays, I use NumPy. The workflow followed the four main steps given here. First, I loaded the GML network file into Python. Then I extracted the giant connected component. So this is important because path-based metrics like average path length and diameter require the network to be connected. Third, I computed the network parameters discussed in the lecture slides, including structural, clustering, centrality, and efficiency measures. Finally, I generated the visualization and summary statistics to, interpret the structural properties of the network. Now, we will present the basic structural parameters of the network. First, the order of the network is 4,941 nodes. This makes it a medium-sized real-world infrastructure network, large enough to show complex structure, but still computationally manageable. The size is 6,594 edges. Compared to the number of possible connections in a network of this size, this is very small. The average degree is 2.67. This means that on average, each station connects to fewer than 3 others. This clearly indicates sparse connectivity. The degree range is from 1 to 19, minimum and maximum. Most nodes have very low degree, but a few nodes connect to many others. This suggests the presence of hubs, although not extremely large ones. Finally, the density is 0.00054. This confirms that the network is extremely sparse. Only a tiny fraction of all possible edges actually exist. Next, we will talk about the path-based metrics that describe a global connectivity. Here, these metrics describe how far nodes are from each other in the network. The average path length is approximately 18.99. This means that on average, it takes about 19 transmission steps to connect two random substations. This is relatively long compared to social networks. However, it makes sense for geographically distributed infrastructure system like this. And the diameter is 46. This represents the maximum shortest path distance between any two nodes. So the longest minimal transmission chain in the network spans 46 steps. Global efficiency is 0.0629. Efficiency measures how easily information can move through the network. This low value suggests limited availability of short alternative routes. Overall, these results show that the network is connected but stretched across space. Now we will talk about the clustering properties and small world characteristics. The average clustering coefficient is 0.0801. This means that triangles exist in the network, but they are not very common. Global clustering coefficient is 0.1032. This is slightly higher than the average local clustering, and it shows that some triangle formation at the global level. And compared to social networks, these values are modest. This is expected because infrastructure systems are not built to maximize triangle formation. The proximity ratio is 134.96. This compares the clustering and path length of this network to a random graph with the same size. And a value much greater than 1 indicates strong deviation from randomness. Here, despite having long paths, the network is significantly more clustered than a random graph. This suggests structured organization rather than random wiring. It's obvious because this is a real thing. And finally, we'll talk about the centrality and critical nodes. Here, the average betweenness centrality is very small, about 0.00364. This means most nodes do not lie on many shortest paths. However, the maximum betweenness is 0.2884. This is significantly higher than the average. This tells us that a small number of nodes act as major bridges between regions. These high betweenness nodes are structurally critical. They play an important role in maintaining connectivity across the grid. If such nodes fail or are removed, the network could fragment or experience serious disruption. This is very important for infrastructure resilience analysis. And now we are going to look at the visualization. And this figure shows a visualization of the Western US power grid network. Each dot is a substation or power station. Each line is a transmission connection. To generate this, I use NetworkX sprint layout with a fixed seed. This is a force-based layout. That means connected nodes are pulled closer and unrelated nodes are pushed apart. So it doesn't show geography, it actually shows the structure. For communities, I used greedy modularity community detection. This method partitions the network to maximize modularity. The algorithm found 43 communities and I colored nodes by their community ID. And in the figure, we see a dense central region and multiple peripheral branches. This supports the earlier results. The network is sparse, modular, and not random. Now, to summarize the analysis, the Western US power grid is a sparse but fully connected infrastructure network. The low average degree confirms that most substations connect to only a few others. The long average path length and large diameter reflect geographic and physical constraints. Unlike social networks, power grids cannot create shortcuts arbitrarily. The clustering values are moderate. This indicates some local redundancy, meaning small groups of substations are interconnected. However, the network doesn't exhibit strong social network style cohesion. And the centrality analysis revealed that a small number of nodes have very high betweenness. These nodes act as structural bridges between regions. Their failure could significantly impact connectivity. Finally, the detected community structure shows that the grid is modular. It is clearly not random. Instead, it reflects organized regional segmentation. And in the next slide, I will talk about the challenges for large-scale network analysis. So this network is moderate in size, but normally large-scale networks introduce additional challenges, such as computational complexity becomes a major issue because there are like, when you calculate those metrics as identity metrics and like when you get the inverse value and all, those are really computationally expensive. Path-based metrics such as average shortest path length and between a centrality scale, like those are, when the system is really large, they scale poorly. So that's a problem. And for very large networks, the computations becomes expensive. Sometimes we get a sample and do the calculations, because if we want to calculate the entire graph, like do some calculations on the entire graph, those exact computations are really expensive, takes hours. Second, memory constraints become significant. So the dense matrix representation are not feasible for large graphs, especially when the network is sparse. Third, visualization becomes difficult. It's really hard to visualize things when the network size increases. So the full network layouts become cluttered and hard to interpret meaningfully. Fourth, real infrastructure networks are dynamic. We know that they evolve over time, which means static graph analysis may not capture temporal behavior. Finally, data quality is also critical. Missing, outdated, or uncertain connections can significantly affect the metric accuracy. These challenges highlight the need for scalable algorithms and careful interpretation in large network analysis. And this is the last slide. This analysis uses the Western US power grid dataset. And I think it was compiled by Paula, and I found it here. So all the results in this presentation are based on this dataset. Yeah, thank you.